Hello everyone, I'm Shambhavi, and today I'm presenting to you my project on electrochemical sensing of dopamine using titanium dioxide nanoparticles. Now, one may ask, why do we need to sense dopamine? Well, it is for a fact that dopamine is essential to us humans. Any kind of imbalance in our dopamine levels can make us feel sad, tired, or even make us fall sick, making it really important that we're able to sense dopamine. Coming to our objective. Our objective was to be able to synthesize titanium dioxide nanoparticles, then characterize them using many different spectroscopic methods, and then evaluate its sensing. Why titanium dioxide nanoparticles? Well, there are some properties of titanium dioxide nanoparticles that are ideal for sensing, such as its biocompatibility and how it causes minimal harm to the environment, its large band gap and its plus 4 oxidation state, the high surface area it has, and also the cost effective synthesis. We can produce titanium dioxide using methods like sol gel and hydrothermal and still ensure high purity and uniform particle characteristics. Here are some of the material properties of TiO2. TiO2 has many crystal phases such as anatase, rutile, bruchite. However, we obtain the rutile crystal phase. It also has a very high melting and boiling point, which represents high thermal stability. It also has excellent electron transfer properties. And here is how we synthesized it. We first added isopropanol and water, to which we then added titanium tetraisopropoxide dropwise to the solution at 80 degrees Celsius. This was then left to stir at constant temperature for an hour. After an hour, we then added nitric acid after lowering the temperature to 60 to 65 degrees Celsius. This was then left to stir for about 5 more hours for the gel and the nanoparticle formation. After 5 hours, it was then centrifuged at 9,000 rpm and with first water then ethanol to remove the impurities. It was then dried at 80 degrees Celsius and calcinated at 200 degrees Celsius, such as XRD. This showed us 8 different characteristic peaks with a confirmed tetragonal crystal system. The average crystallite size was 4.21 nanometers, which is optimal for high surface area sensing. Coming to the thermogrammetric analysis, the overall weight loss was 50.9%. However, most of the weight was lost, about 43.9%, within 500 degrees Celsius, and 7% of the weight was lost between 500 degrees Celsius to 800 degrees Celsius. This shows that the thermal properties of the remaining sample above 500 degrees Celsius are pretty good. Coming to the zeta potential. The zeta potential graph, as we can see, is very pointed and tall. This tells us that the charge is uniform in the sample. And as we can see that the zeta potential is about 41.21 millivolts. This tells us that the sample is highly stable and also positively charged. The BET analysis told us that the sample has a surface area of about 36.841 and an average pore diameter of 20.77. This allows the biomolecules to be able to enter the pores and react. These are the images of the scanning electron microscope. As we can see, the morphology is not very clear of the TiO2. However, the images from the transmission electron microscope show us that TiO2 formed a needle-like structure. Coming to the electrochemical setup, we use cyclic voltammetry to test the redox behavior and sensing capabilities of TiO2 with dopamine. And it was a 3 electrode electrochemical setup, and the working electrode was a glassy carbon electrode coated with TiO2 nanoparticle slurry, which was made of TiO2 nanoparticles, Nafion binder, and ethanol. The reference electrode was an AgAgCl electrode, which provides a stable reference potential. And the counter electrode was a graphite carbon standard electrode. The electrolyte medium was a phosphate buffer solution of pH 7, and the voltage range was from about 0.4 volts to 1 volt. The ions of the analyte carry current on oxidation or reduction of the dopamine molecules. And this current is proportional to the concentration of the analyte when the current is diffusion limited. As the voltage varies, current peaks for oxidation. The smaller peaks are for reduction. The position of the graph depends on the properties of the analyte, and the intensity depends on the concentration. And that is it. I would like to acknowledge some people for supporting me throughout this project. I would like to acknowledge Prayoga Institute of Education for providing the facilities and the equipment for this project to happen. I would like to express gratitude to my school for supporting me. I'm also grateful to my teammates and mentors for working with me during this project. And lastly, I'm also thankful to my parents and friends for supporting me. Thank you.